Have you ever wondered how a semiconductor device, once activated, can reliably control large amounts of power without needing a continuous trigger signal? It is quite fascinating how they effectively manage electrical flow with such precision. Once an SCR, or Silicon Controlled Rectifier, is triggered into its conductive state, it maintains forward conduction current through a self-sustaining process known as latching. This means that even after the gate trigger signal is removed, the SCR continues to conduct as long as the anode current remains above a critical value called the holding current. The core mechanism behind this maintenance of conduction lies in the SCR's internal structure, which can be modeled as two interconnected transistors, a PNP and an NPN, forming a positive feedback loop. When a trigger current is applied to the gate, it turns on the NPN transistor. The collector current from the NPN then acts as a base current for the PNP transistor, turning it on. In turn, the collector current from the PNP transistor feeds back as base current to the NPN, reinforcing its conduction. This regenerative action quickly drives both transistors into saturation, creating a low-resistance path for current flow from the anode to the cathode. To stop an SCR from conducting, you must interrupt this positive feedback loop. The primary way to do this is by reducing the anode current below its holding current level. This can be achieved by either opening the main circuit, thereby breaking the current path, or by momentarily applying a reverse voltage across the anode and cathode, which forces the current to drop to zero and allows the internal charge carriers to recombine, effectively turning off the SCR. In AC circuits, the natural alternation of the current waveform often provides this reverse bias automatically, causing the SCR to turn off at each zero crossing. It is important to differentiate between latching current and holding current, as these terms describe distinct thresholds. Latching current is the minimum anode current required for the SCR to remain in conduction after the gate trigger is removed and before it reaches its full on-state current. Holding current, on the other hand, is the minimum anode current required to keep the SCR conducting after it has fully turned on and reached its steady state. The holding current is always less than the latching current. Understanding this distinction is vital for proper SCR circuit design and operation. Ultimately, the SCR's ability to maintain forward conduction current through its intrinsic latching mechanism makes it an invaluable component in power control applications. By understanding the regenerative feedback loop and the critical role of the holding current, you gain insight into how these robust devices efficiently manage electrical power, ensuring reliable and precise operation in various systems.